hello. Good evening, good morning, good afternoon to all of my continents: Asia, Africa, Europe, South America, North America, Australia, New Zealand, um, Antarctica. Now I am naming more than just continents. At some point, I also named Madagascar. Thank you so much, Mauritius. You know, I feel like I've not always done justice to the great continent of Africa. So I want to make sure that I call out Africa every time. It is a continent that I have yet to visit myself, and so forgive me if I don't know too much about it as of yet. But thank you so much for being here. Hopefully, you're joining from all across the world very soon here on my live on this live stream episode tonight. It is nighttime here in North America. Welcome. If you're joining, please do put something in the chat. I hope to meet many of you tonight. That is both old and new friends. Thank you so much for liking the live. Thank you. Please do like, share, subscribe. Tell your neighbors, tell your mother, tell your father about this live stream, which is gonna, of course, include physics and kitty cats, but mostly probably physics. I mean, Baji is here with me providing a lot of moral support. Hi, Jeep. Hello, Jeep says hi, and Jeep is saying I was the first like. Thank you, Jeep. How are you doing? It's been a hot second since I've seen you on here, and it's very lovely to have you here. How are you doing? So tonight we're actually going to talk a little bit about dark matter and the evidence of dark matter in the form of orbital speed versus distance from galactic center of objects in our own galaxy, in our own home Milky Way galaxy. So we'll touch upon that. We have actually talked about this in the past as well, but it is an important topic and evidence of dark matter, and we can, if we have time, we can even talk about some dark matter candidates as well. But because we were talking about black holes yesterday, it kind of came up. We actually talked about quasars last night, and it kind of came up as far as galactic centers of other galaxies like our galaxy, as well as black holes in general, and this is kind of related. So we will make use of this and talk about that tonight. Talk about hot chocolate instead. So how are you doing, everybody? Thank you so much for being here and saying hi in the chat. I do appreciate it. Let me make sure and share the live on my channel as well. Thank you. Thank you for liking the live, and thank you for being here. And if you're seeing this as usual as a video upload later on, please do leave something in the comments for me to read later on, and I much appreciate all your support. Thank you. Okay, and also please like, share, and subscribe as usual. Let me see. Let me put like and share, and then let me also put like and subscribe. Acacio, that's me. Believe it or not, I'm back. Acacio, oh my gosh, how have you been? Here we are, my friend. Muchas gracias for joining. How are you doing? Here I am, and here you are. You're back from where? Last night you were not there. We were very sad. Like and subscribe. That's me. The moon. Have you been in the moon? Oh my gosh. I am so very happy to see my friends. We are live. I will put it in the chat. Well, not the chat. I will put it on my channel. And usually I wait and say hi to everybody that's joining, and we chit chat for a little bit, but I might just go ahead and start the topic in just a second here. Ooh, I will pin my message that says to like and subscribe. There we go. Thank you for joining. And okay, so let me recap. Acacia says, I was there and I gave you my like, but I was falling asleep. Oh, I'm sorry. So we won't stay too late tonight. I understand people have to go to bed. So how about we quickly talk about our own galaxy and the orbital speed versus distance from galactic center of the objects and the evidence of dark matter, and say hi to everybody, and then we will wrap it up in an hour or so. Okay, what is this live stream about? This is going to be about astronomy, physics, astrophysics, cosmology, but more specifically tonight we're talking about dark matter evidence and probably some dark matter candidates. So this channel, we discuss physics and cats. We show cats, we show myself, and we talk about physics. And mainly we cover astrophysics, astronomy, cosmology, astrophysics, astronomy, cosmology, physics. Yeah, those topics under physics. Please do like, share, and subscribe. Please double tap the screen and give us some likes. Thank you so much. We will get started. Hello, Chris. Hello, Wayland. Hello, Jeep. Hello, everybody. What's dark matter? That's exactly what we'll talk about. So we are part of the Milky Way galaxy, and there is a supermassive black hole at the center of our own galaxy. Now, there were some interesting ways in which this was found. We actually found that even though black holes are black, as in even light cannot escape a black hole, at least classically speaking, sometimes a black hole can give itself away by having things around it that's kind of falling into the black hole. And because of the acceleration of those particles that are falling into the black hole and getting accreted by the black hole, there is sometimes some immense emission from those particles coming out. For example, synchrotron radiation from the acceleration of those particles. Sometimes these particles can be falling into the black hole at relativistic speeds. So speeds at which you would have to account for a special theory of relativity. For example, speeds that are not the speed of light, but closer to the speed of light than classical. So very interesting sort of phenomena, very, very almost festive, but in a kind of brutal way. Lots of things falling, accreted getting into the black hole can be happening sometimes. And depending on exactly how things are falling, you actually get very bright emission from around where a black hole is. And this can actually give away that there is a black hole there. So this is actually how sometimes we discover black holes, because you can, and this type of radiation that I speak of can be in multiple wavelengths. It can be in X-ray, it can be in radio, it can be bright, and that too in multiple wavelengths. So this is sort of how we discovered the galactic center supermassive black hole of our own galaxy. And of course, we think that most galaxies actually have such a supermassive black hole. So as you might imagine, this supermassive black hole is a big deal in our galaxy. It really affects things, and objects in our galaxy are kind of in orbit around this black hole. The other thing I wanted to mention is that black holes have been known about for a long time, over 100 years, soon after I believe Einstein gave us general theory of relativity. Basically, general theory of relativity can be solved exactly for black holes in the classical physics way. And so it was theorized a long time ago, but no one actually expected. So this is a tidbit, little fun fact, that nobody actually expected that black holes would actually be a reality and be out there in nature, in the wild, and that we would actually start to discover these black holes, But slowly but surely, more and more interesting things have been getting discovered, and especially when neutron stars, which is a type of stellar remnant as well, because there are 3 types of stellar remnants. These are white dwarfs, neutron stars, and black holes. So depending on exactly how extreme the collapse of a star is, when it dies, you can make a black hole, or you can make a white dwarf, or you can make a neutron star. Is my audio okay? Can people hear me? Acacia, can you confirm whether I can be heard or not. So basically, those are the three stellar remnants, and depending on the mass of the original star that dies and collapses into such a remnant, you actually might get a black hole. But even though this was theorized and general relativity, Wayland says, I can hear you. Thank you, Wayland. Even though it was theorized that we expect to have black holes in nature, nobody expected to find them because they seemed very crazy. But guess what? We actually discovered them. And as I was mentioning about the supermassive black hole at the center of our own galaxy, of course, it was discovered. And sometimes the brightness around the black hole, because of the stuff that's falling into the black hole, is precisely how we actually discover the black hole. And that's how it was discovered here for our own galaxy as well. So now, related to supermassive black hole in our own galaxy, let's see some interesting phenomena that may or may not be going on in our own galaxy, which actually gives us an evidence, a very strong evidence for dark matter, and that too, dark matter in our own galaxy. Okay, so that's what is the main topic for tonight. So are black holes possible to contain? Contain, I'm not sure about what you mean by contain, but black holes are definitely possible in nature. They are definitely a thing in nature, and we have been finding them and observing them. But I'm not sure what do you mean by contain. You can say more about that. Like able to control. Not that I know. I don't think so. So not that I know. I think black holes may contain us, but I don't think we can control a black hole all that easily. Can we control them in any way? Probably not. So I'm actually going to do a little exercise with you guys and share some Python code I've written to show you tidal forces on a body because of a black hole. And so if you're near a black hole, and if you're able to kind of experience the gravitation of a black hole, then it can actually be very dangerous. And depending on the mass of the black hole, you will experience tidal forces from head to foot as well as sideways. And depending on the mass, again, of the black hole, in astronomy, you will notice that a lot of things depend very much on the mass, like pretty much very simply on the mass of the object. So black holes are no different in this case. The mass of the black hole is immensely important. And so actually turns out that the smaller mass black holes are even more dangerous. And it all comes from the Schwarzschild equation for a black hole, which we'll touch upon here right now. And the smaller mass black holes can exert a lot of tidal forces on a body, on say a person if you're nearby, and kind of rip you apart. So that's why I would say if you're going to jump into a black hole, to try to do something like contain it, control it, or observe it, you might want to pick a more massive black hole versus a smaller black hole. You might want to pick, for example, a supermassive black hole, because there actually the tidal forces are very minimal. Okay, so, and to prove this, I actually have an exercise for you guys that I will be sharing soon as I kind of put it together. I just have to put some slides together and whatnot. Okay, noted. I'll try that later. Yes. So, I mean, in all seriousness, if we do get the technology to go near a black hole, I think currently we're also limited by the fact that we don't travel very far. We don't really travel far enough to get to a black hole. We don't travel astronomical distances. I mean, even going to Mars is such a big deal, and Mars is very much sort of in our local neighborhood. It's in our solar system, and that too in the inner planets. So imagine if going to Mars is such a big deal, then going to a black hole would be a really big deal, you know? So I think the distance is a limit at this point, a limitation at this point. But if you do gather the technology to visit a black hole, I would definitely pick a supermassive black hole for your safety reasons. And don't cross the event horizon. If you stay outside of the event horizon, then the tidal forces on a person due to a supermassive black hole is not too bad. Okay? Now, if you cross the event horizon, then you won't be able to get out. So That's why I say don't cross the event horizon. But then if you're really curious and you want to cross it, then by all means, but just know that you probably can't share that information with us again, because nothing really, the information won't come out of the black hole. Thank you so much for visiting, and please do like, share, and subscribe. Please give us a like, double tap, and subscribe for more. We go live and we post a lot of content, videos, and shorts on all these types of topics, okay? But yeah, pick a supermassive black hole. It's gonna be great. So, next we will talk about our own galaxy and certain motion of objects in our own galaxy around the galactic center. So did you guys know that we're all kind of orbiting? So you know how the moon is orbiting the Earth. The Earth is orbiting the sun. Well, the sun is actually orbiting the galactic center of our own galaxy, okay? So, and I mean the sun along with all of us, planets and everything, we're all orbiting our galactic center. And we will talk about some of the distances and whatnot, like how far we are from the galactic center, blah, blah, blah. But basically, it's actually, that's how things kind of work. We've got that supermassive black hole. The galactic center has big mass in it, huge mass in it. Millions of suns worth of mass in the galactic center, and we're all orbiting around it. And the sun actually has orbited our own galaxy's galactic center only about 20 times. So in that sense, the sun is a 20-year-old young adult in terms of stars and things like that. So we will kind of look at that, okay? So let's see. So we are referencing, by the way, this book called Foundations of Astrophysics. This is by Barbara Ryden and Bradley M. Peterson, professors at Ohio State University. Very nice people. Let's see. Okay, so this book has an excellent picture of the Milky Way galaxy, which is of course a spiral galaxy, but also know that an excellent picture of the Milky Way spiral galaxy is an artistic picturization. Because we're in the galaxy, we can't quite take a nice photo of our own galaxy, if that makes sense. We can take nice photos of other galaxies that are not our galaxy, but anytime you see a Milky Way galaxy picture, that is sort of an artist's rendition, is that a word? It's not going to be a real photo, okay? Because we are in the galaxy. So if we would have to send the camera out of the galaxy and then take a photo, which we haven't done yet, if we wanted a photo of our own galaxy, you know, from and see the full spiral and all that stuff. So let's see the sun's orbital speed. So there are some numbers that we're going to talk about here. So hang in there, hold tight. It's going to be great. And it's just a little bit of information. So this is not going to be very long drawn. And I do have to reference the book. There's a few numbers here. So I just mentioned that the sun is going around our very own galactic center, orbiting the center of the galaxy. That's a great question. We will come back to that. So the sun's orbital speed around the galactic center is estimated to be V naught equal to 220 kilometers per second. So 220 kilometers per second is, in other words, 225 kiloparsecs per giga-year. So the parsec is an astronomical unit of distance. Kiloparsec is basically 10 to the 3 of that. So oftentimes we say things in parsecs, kiloparsecs, megaparsecs. Kiloparsec is sort of the order of the length of a galaxy, or several kiloparsecs is generally the length of a galaxy like ours. Megaparsecs would be something like something extragalactic away, you know. And then we sometimes have gigaparsecs. We actually have events, transient events in the sky called gamma ray bursts. Those kind of happen order of like gigaparsecs away. So parsec is something, just get comfortable with the notion of it. You can even Google it and see exactly what it is, what the unit is. But pretty much oftentimes we say things in terms of parsecs and sometimes giga-years, because giga-years is of course is a billion, 10 to the 9 years. And because this is astronomy, long times, long distances, so we will say this in that. Okay, so the orbital speed, so the sun, our solar system going around the galactic center, orbital speed is 225 kiloparsecs per giga year. So every giga year, 225 kiloparsecs is the distance it will travel. So later on, we'll discuss how the orbital speeds of the sun and other stars are actually determined. So this will be later in the book, later in discussion, not tonight. For now, let's just consider the implications of this orbital motion. The distance of the sun from the galactic center is R0 of 8 kiloparsecs. So if you're wondering sort of where we are, we're not actually at the galactic center, thank God. The galactic center is quite an exciting place, probably not the safest for us. And so we are a little bit off to the side, actually. We're sort of not really part of the center of our own galaxy. We're not even that close to the center. We're a little bit to the side, okay? So we are at 8 kiloparsecs. So the sun orbital radius is 8 kiloparsecs. So, and we're all going around the sun. We're very much a part of the sun's family. So we are all 8 kiloparsecs away from the galactic center, and going at a speed of that 225 kiloparsecs per giga year. Hi, Shamanen Tanzer. Okay, hello, sorry about that. Sorry about the pronunciation. If we make the approximation that the sun is on a perfectly circular orbit, so we're going to make this approximation that the sun is at a perfectly circular orbit of that 8 kiloparsecs away from the galactic center, we find that its orbital period is 0.22 giga years. So the orbital period is 0.22 giga years. During the sun's 4.6 giga year lifetime, so the sun is a pretty young star of only 4.6 giga years or 4.6 billion years old, similar to our age. We're all about 4.6 as in our planet's age, Earth's age. So during the sun's 4.6 giga year lifetime, it has gone around the galactic center just over 20 times. So from its period, we get this. So as I was saying, the sun is quite young in terms of its exploration in this galaxy as well. It's gone around the galactic center only about just over 20 times. So in that sense, it's a young adult. To find out how much mass is inside the sun's orbit, we may use Kepler's third law. So Kepler's third law, hi Stephen. Kepler's third law is something that we can use even for this. So we have mass of the sun plus mass of G, which is the mass inside a sphere of the radius that we're considering. That's going to be equal to a to the cube over p squared. So as you might be familiar, Kepler's third law gives us a relationship that kind of connects the masses of something to the semi-major axis of its orbit and the period of that orbit. So that's what this is. So all the mass is on the left side, and then the right-hand side has a cubed over p squared, where mg is the mass measured in solar masses here inside a sphere of radius 8 kiloparsecs in this case, because we want to consider our own orbital radius from the galactic center, centered on the galactic center. A is this A, the semi-major axis, or in this case, we're considering a circular orbit, so same thing, is going to be 8 kiloparsecs. And the P is going to be that period, so 2.2 times 10 to the 8 years, which is the period. Strictly speaking, it must be confessed, we can only use Kepler's third law if the two bodies involved are spherical. So this is a bit of an approximation that we're making, because strictly speaking, Kepler's third law is for spherical bodies. And this is sort of not really spherical, right? It's sort of a distribution. So since the matter distribution of our galaxy is flattened, the mass mg computed from this equation we just talked about will be slightly inaccurate. Still, it will be good enough for a first estimate. We're just trying to get an estimate. Since the mass of the galaxy is much greater than the mass of just one star, we may assume that mg is much, much greater than m solar for that equation we had. And we can just kind of say that mg plus m solar is approximately equal to mg, because, the sun's mass is in there, but mg is all of that mass contained within the 8 kiloparsecs. So let's just forget about the m solar. So drop that. So 93. So after this, we can actually solve, right? Because now we have mg is approximately equal to a cubed over p squared, where a is 8 kiloparsecs, p is the 0.22 gigayears. And so now we can solve for mg, and we can get what mg is, thank God. Because we've done a few approximations, but it's okay. We can still find out. So what is mg? mg is 9.3 times 10 to the 10 solar masses. So we're getting all the masses in terms of our sun's mass. And this turns out to be 9.3 times 10 to the 10. 10 to the 9 is a billion, so 93 billion. 93 billion solar masses is that mg. So all of this was to figure out what is the mass that's within that 8 kiloparsecs. It's 93 billion solar masses. So it's a lot of mass, especially when you consider that the total luminosity of our galaxy is merely 23 billion solar luminosities. So we're thinking that 93 billion solar masses is quite a bit of mass, because we have an estimate. We also have an idea for the luminosity of our galaxy. Luminosities is something very important in astronomy. Pretty much, if there's a source, if there's an object that's from which we can get light, we would like to know its luminosity. So we know the luminosity of our galaxy is only 23 billion solar luminosities. So the material of which our galaxy is made must have, on average, a higher mass to light ratio than the sun. Because if all that mass is producing only 23 billion solar luminosities, then our sun, basically that mass versus the light, must be kind of high for other things in the galaxy. This would sort of suggest that. The material of which our galaxy is made, once again, on average, a higher mass to light ratio than the sun, because the sun's, sun's mass versus sun's so luminosity seems to be kind of different than that 93 billion solar mass versus the 23 billion solar luminosity. Moreover, the mass mg equal to 9.3 10 to the 10 solar masses contains only the mass inside the sun's orbital radius. So this is only for the 8 kiloparsecs. So within the 8 kiloparsec orbital radius from the galactic center is this 93 billion mg, the 93 billion solar mass mg. So that's a lot. The mass outside the sun's orbit has no net effect on the sun's orbital motion, assuming that it's spherically distributed. For stars and gas in the disk of our galaxy to be on stable circular orbits, we require that V of r squared over r is equal to gm of r over r squared. So where g is the Newtonian, is the gravitational constant of nature, gravitational constant of nature. So this v of r that we have just now defined, or just now put in that equation, is the orbital speed of a star on an orbit of radius r. So we know this type of relationship for the orbital speed of an object based on its mass and radius and the gravitational constant. So v of r is the orbital speed of a star on an orbit of radius r, and m of r is the mass inside a sphere of radius r on the galactic center. So basically, this thing, v of r squared over r, is equal to gm of r over r squared. This is basically what we expect for things that are within that, for the masses that are within that orbit of radius r. We're kind of generalizing now. The 8 kiloparsec is our sun's radius from the galactic center, but for just in general, this is what we expect. And m of r is the mass inside a sphere of radius r centered on the galactic center. We can thus determine the mass inside a star's orbit from its orbital speed v. So now this is another way of basically figuring out the mass, just like what we did for the sun and the sun's orbital radius and all that. we can in general say that m of r is equal to v of r squared times r of over g. So we basically have a simple equation to tell us what mass is within that orbital radius based on its orbital speed. So if you have the orbital speed of something and you know what radius it's away or what distance it's away from the galactic center, you actually should be able to tell the mass contained in that sphere. Most of the galaxy's luminosity, so now we come to, again, the luminosity of the galaxy, because we know about the luminosity of the galaxy. Most of the galaxy's luminosity is provided by the disk. So our galaxy has this part called the disk, whose brightness falls off exponentially with a scale length Rs, which is equal to 3 kiloparsecs. So within 3 kiloparsec is most of the luminosity. Thus, most of the galaxy's luminosity lies inside the sun's orbit. Because the sun's orbit is at 8 kiloparsecs and the luminosity falls off exponentially after 3 kiloparsecs, all of that is to say that well within the sun's orbit of the galactic center is most of the luminosity of this galaxy. Wow. If most of the mass lies inside the sun's orbit as well, we would expect that the mass would be about constant for when the radius, when you go farther away from the distance, from the center of the galaxy. So when r is much, much bigger than r naught, then you would you should basically have constant mass, because that is coming from that relationship of the mass going as v squared r over g. So because we have that relationship already, and we're seeing that most of the luminosity, okay, is well within the sun's orbit. So most of the mass of this galaxy should be within the sun's orbit. And so we would expect the orbital speeds to kind of just like fall off as you go farther and farther out. Observations, however, of stars and gas clouds in our galaxy reveal, so this is the kicker, this is the important observation. Observations of stars and gas clouds in our galaxy reveal, however, that the orbital speed v in the disk does not fall off with distance from the center. This is where things get very interesting. We would expect that if things were just according to what we understand, and we've got this relationship between the mass within a certain orbital distance from the center, we've got a relationship between that mass that's contained within a certain radius of the galactic center and its orbital speed of any object that is within that radius. We have a relationship that v basically goes as r to the minus 1/2, because we would expect that the mass would be kind of constant, because most of it should be kind of inside that 8 kiloparsecs. In fact, most of the luminosity is within like 3 kiloparsecs, quite close to the galactic center. Given all that, we would have expected that the orbital speeds of things would just continue to fall off as you go farther and farther away from the galactic center. But that does not happen. It does not happen that way. So things get interesting, because instead of the orbital speeds falling off away from the galactic center, what we find is that all the way to the outer fringes of the disk, the orbital speed is constant or even slowly rising with radius. Orbital speed actually starts to rise with radius, which is quite a mystery. I have a plot of this that I can show you, and I've shown it before. You would expect for the Keplerian consideration, if just classical physics, how we know it. Hi, Amir. classical physics, Keplerian physics would say that the orbital speeds should kind of go like this as you go away from the galactic center, like this. So if you have orbital speed in the vertical axis and you have distance from the galactic center, the Keplerian way would say that it would kind of fall off. But instead what we see is that it goes like that, as in it goes up at some point after being constant. Very interesting indeed. Incredible, says Amir. Absolutely incredible. This is not what we expected, especially keep in mind, because we saw that most of the luminosity of the galaxy is within 3 kiloparsecs of the galactic center. Goodness gracious. So basically, I mean, in the galaxy, there are stars, there are objects, and we kind of expect that, like, if we didn't know about dark matter, and we still don't fully understand dark matter. So if you're not considering things that are dark and not contributing to luminosity, I mean, some things are kind of darker, like certain compact objects actually are not very luminous, right? That's okay. But there is sort of this intuitive feeling that whatever is producing all of the luminosity is probably all of the mass, right? So pretty much people thought they were confident that because most of the luminosity is contained within 3 kiloparsecs, that's where all the mass is. And definitely as you go farther out from the galactic center, the orbital speeds would be going down. But that is not the case. That is not the case. The orbital speeds are going up. Okay? John Foster says, did you write a book? Hi, by the way. Hi, John Foster. Emir is saying, do you have a website? I do. It's called howtophd.org. I have a website. It's a blog, and it is called howtophd.org. I also have YouTube right here. Please do like, share, and subscribe. I also have Instagram, TikTok, all of that. And John Foster is asking, did you write a book? I did write a few books. It's there on Amazon. So yeah, thank you. I don't have a book. I don't have a book on this stuff yet. I have a book on gamma ray bursts. I actually have a short review, utilizing lots of sources, of course, on gamma ray bursts. It's a topic from my PhD. And I have other books, all on Amazon. If you check with my name, you can find them. But also, most of the content in my books is also in my blog, howtophd.org. So you can also check that out. I used to have like a mailing list. I don't even do that anymore. So, it's all free, up to you. Check it out. Thank you. And the blog is a little bit not so active right now, but I will add more information soon here. It's been going on for many years though, so you have a lot of reading to do if you want to go read the blog. So yes, thank you for asking. Website howtophd.org, and books are on Amazon. And the website howtophd.org also tells you about the books. So if you're looking for the books, you can find them. I have 3 ebooks on my website. Oh, very nice. Thank you for sharing, Amir. Amir Valejos, I'm subscribed. I've been here before. Oh, thank you so much. Oh, thank you. Oh, that is very nice of you. Very kind of you. Thank you. Okay, so intuitively, without really expecting dark matter, when you see that the luminosity of the galaxy is contained within 3 kiloparsecs of the galaxy, you would expect that is where all the mass is. But instead now we're finding mass away from the galactic center. Goodness gracious. What could this be? Okay, so people did not expect, like the halo is the outer parts of the galaxy, or all around the galaxy, right? People did not expect there to be a ton of mass in the halo. It's dark there, It's dark. It looks like there is nothing there. So there's 2 ways in astronomy that we can observe things. Well, there's probably, there's more ways. Let's just, for the sake of this argument, there are two main ways to know that there is something somewhere. One is with electromagnetic radiation, so light. If something gives off a luminosity, you can say, oh, there is some things there. Oh, there is a bright spot in the sky there. It could be in a different wavelength than what you can see with your eye. It could be in radio wavelength. It could be gamma rays, right? But if you have got a spot in the sky that is giving off gamma rays, hurting your eyes, or you're picking it up with your instrument, you know something is there. If something gives off radio waves, you know something is there. The other way to know something is there is through gravitational effects. If with gravitationally you feel something, like it feels like it is affecting things around it gravitationally, then that's the other way of knowing that something is there. This is that way. Basically, light-wise, as far as seeing things, the halo is dark. Most of the luminosity, once again, is towards the galactic center. It is within 3 kiloparsecs of the galactic center. So gravitationally, we feel and we observe that there is something more, but we don't see it, okay? We don't see it electromagnetically and with light, okay? So, and why I say that there's probably more ways is because there's also particles. So another thing to keep in mind, you want to see something in astrophysics, you want to see something either with gravitation or with light or electromagnetism, or actually you can get particles from things as well. There could be a spot in the sky that's spewing neutrinos and nothing else. I mean, that would be weird. I mean, that could be a little weird. But if there is a spot in the sky that is giving you a ton of neutrinos, but nothing else, which would be a little weird, but it could happen, I guess, then that is another way to know that there is something there, okay? So with you are social media, YouTube and website. No, I have everything. I have Instagram, I have Facebook. It's all linked in my YouTube description. On my YouTube description, you can find Instagram, TikTok, Facebook, everything. It's all there. Hi, Ashutosh. We can talk about the God particle. So basically, in astrophysics, either you know something, you observe something with light, the electromagnetic wave spectrum, it could be any kind of light, or you know things gravitationally, or you know things with particles. So, you know, dark matter, this is basically going to lead us to dark matter, right? This thing where we see more mass, but we don't see it, we feel it with gravitation. If dark matter particles were to be discovered, that's another way of observing dark matter. So getting some kind of particle is also a legitimate way of knowing that something is there, okay? Or something is happening, some event is happening, or there's an object or a source or something. But it has to be something, right? And we were not expecting this gravitational finding of extra mass in our own galaxy. So all the way to the outer fringes of the disk, the orbital speed is constant or even slowly rising with radius. Oh my gosh, rising with radius, as in there is more and more towards the halo of the galaxy. Thus, there is more mass outside the sun's radius than inside. Goodness. We thought that we were alone over here. Oh, thank you so much, Acacio. Oh my gosh, Acacio has done a super chat. Thank you so much, guys. If you're doing a super chat, I really appreciate it. Helps to keep the channel going. Thank you so much for doing a super chat. So we are at 8 kiloparsecs from the center of our own galaxy. We might have thought that we are alone. We're alone here. Most of the stuff is inside 8 kiloparsecs, 3 kiloparsecs. We are so lonely. That is not the case. There is more mass outside the 8 kiloparsecs than there is inside the 8 kiloparsecs. Oh my gosh. Not what we expected at all. Not what we expected at all, okay? Thus, there is more mass outside the sun's radius than inside. If we estimate what this is, we actually find the mass inside 16 kiloparsecs. So now let's back up in the galaxy and go to 16 kiloparsecs. So if you plug and chug 16 kiloparsecs, we actually find that there is 2.7 times 10 to the 11 solar masses. 2.7 times 10 to the 11 solar masses. What did we say for the 8 kiloparsec? We said within 8 kiloparsecs there was 93 billion. 93 billion solar masses was within 8 kiloparsecs. Within 16 kiloparsecs, we have even more. So we have 2.7, so that is 270 billion solar masses. Oh my God. 2.7 times 10 to the 11 solar masses. That's a lot. Since V is roughly constant outside the sun's orbital radius, the mass must increase as m kind of goes directly proportional as r, implying an average mass density rho that goes as r to the minus 2 in a region where the luminosity density is plummeting exponentially. So it gets dark very fast when you move away from the center of our galaxy. After 3 kiloparsecs, it's dark, dark, dark. Okay. The luminosity is plummeting exponentially while the mass is going up like crazy. So this is called the evidence of dark matter from orbital speed discussions. So dark matter, I should just say, is a research topic. We don't know what exactly is dark matter. We don't know what exactly is the particle nature of dark matter. We will discuss some candidates of dark matter shortly here, but I should let you know that we don't know exactly what dark matter is. But there are a few different ways in which we know that something is out there, or some type of thing is out there that is having a big gravitational effect on things, but we cannot see it with light. So we call it dark matter because it does not interact with light. It's a type of matter that does not interact with light. We have even seen, cosmologically speaking, that it is actually the dominant type of matter in the universe. So ordinary matter, the stuff that we do understand, that is made of particles that we understand, which what we're made of, etc., that is only 5%, whereas dark matter is like 20%. So out of 25% matter, total matter density in the universe, we actually find that dark matter is the dominant type of matter. And that is coming from a cosmological standpoint. So what we just discussed, this orbital speed calculation, observation as a function of distance out from the galactic center, this is a type of evidence of dark matter, and this is astronomy. This is the astronomical evidence of dark matter, and it is also evidence of dark matter in our own galaxy. There are also other discussions that we've had and that we'll continue to have, which are cosmological evidences of dark matter. So this is not just a small topic. We think there is dark matter from an astronomy standpoint, and that's it. No. Dark matter evidence is sort of multifaceted. There are different, it's multidimensional. In other fields too, we see evidence of dark matter. And in cosmology, we have an evidence of dark matter as well. So in cosmology, we actually use both, again, both the electromagnetic spectrum as well as gravitational effects to figure out, oh my gosh, the energy density of the universe is contributed to heavily by dark matter as opposed to ordinary matter. And we've talked about that in our cosmology sessions. So keep in mind that today what we discussed is astronomy. Other days we discuss cosmology, but we always come to the conclusion that there is something that we know not of. Exactly what it is, it's called dark matter because it does not interact with light, and there seems to be quite a bit of it, quite a lot of it in our own galaxy, and it turns out in other galaxies too throughout the universe, and Lots of times it looks like in the halo of galaxies, we get dark matter, okay? Hi, Pranay is saying, hey, where's the hype button? I can't see. You said to press the... Oh, yeah. So in my videos, it might not be here on the live stream or the shorts, but under the video tab and all the videos, there's a new button now that YouTube has. It's called hype. It might be, you might have to scroll, kind of swipe the comments to see it. And there is this button called hype button on YouTube videos. So it might not be something on shorts or live streams, but it's there under the videos. So if you could do that for me, that would be most excellent. Thank you so much for your support, everybody. Pranay, thank you for your support. Thank you. Ashutosh is saying, nice observation, but can we say it's the end of the universe as light doesn't go after that? No. So it is not the end of the universe, because right now what we spoke of is just our own galaxy. So definitely there is much more universe left after our galaxy, right? Because the night sky is full of other sources that are not in our galaxy, right? We see other galaxies, we photograph other galaxies. So we know that we're part of a galaxy, so we cannot take a photo of our own galaxy from the outside, but we do take photos of other galaxies from the outside of those galaxies. So we know that the universe does not end with our galaxy. We know that. But what we're finding is that we have extra matter, which is dark, does not interact with light in our own galaxy itself. And when we consider cosmologically, we also find the same. So we're talking about dark matter tonight. Dusek is asking, D-U-S-E-K. Hi, Dusek. So dark matter is something, it's a very interesting topic because you can study it in astronomy as well as cosmology. So I wanted to point that out. Dark energy is a topic that you'd have to study cosmology because it impacts things at larger scales than what would be traditionally considered astronomy. But dark matter is something that you can attack both from an astronomical point of view, even in our own galaxy, which is quite local compared to the rest, compared to the larger universe. We have dark matter, and you can study dark matter, and you can get this type of evidence of dark matter, as well as it's all pervasive in the universe as well. So, okay. And then, or is it just something that absorbs light? So if something absorbs light, that actually also shows up. So astronomy is all about emission lines, absorption lines, spectra, things like that. So guess what? If you're something that absorbs light, you cannot just get away with absorbing light. So if you absorb light, that also is, we get absorption spectra for when something is absorbed. So you will see like dark lines at places where something is absorbed. So actually, if something absorbs light, we love it because that's another way of knowing that something is there. So like I was mentioning, astronomers are desperate, right? Because we have to depend, our lab is so far away, we have to depend on these sort of indirect ways, absorption spectra, emission spectra, gravitational lensing, something in the way, like there's going to be some kind of solar eclipse. How do we know? Sometimes the earth comes in the way and eclipses the sun or the moon or, all this stuff. It's not like we go to the moon to see the eclipse, right? It's sort of like that. Like there's different ways of knowing something is there or not. And absorption would not be the deal breaker here. So Rishabh is saying, is it possible to build a time machine? Oh gosh, so I don't even know. So dark matter itself is a mysterious topic. And we definitely don't know enough about dark matter to say whether we can build a time machine. Now, having said that, I should point out that going backwards in time So real quick, we'll talk a little bit about cosmology because it's one of my favorite topics. Going backwards in time is actually pretty mundane for particles. So in particle physics, we actually allow particles to go back in time all the time. So in that way, maybe dark matter is also doing that, because we don't even know what the particle nature of dark matter is. So in that sense, I don't want to, say, oh no, that's not possible or something. So as far as like, depends exactly what you want to do. Time machine, I don't know. Do we have a time machine at all of any kind of, any way? I don't think so. But I want you to consider this whole thing about going back in time at different scales. At a macroscopic scale, going backwards in time may not be very possible. But at a microscopic scale, going back in time is actually quite normal. And it happens all the time, pun intended, with particles. And so if there is a particle nature of dark matter that gets discovered, maybe it will go back in time. So who knows? There is no entropy. Hello, last independent thinker. So there is entropy. I don't know what you mean exactly by this comment, but thank you. There is only decoherence. Please do elaborate further. Hello, everybody. Thank you so much for being here. Elaborate further on this comment, but pretty much that's what I'll say. So now, the leading explanation is that there must be dark matter in the outer regions of our galaxy as far as this orbital speed evidence goes, okay? The phrase dark matter is the term used by astronomers to refer to matter that is too dim to be detected using current technology. Dark matter might also be called invisible matter or maybe transparent matter, but dark matter is the name that has stuck. Sometimes it's confused with dark energy. Those are two different things, so don't confuse them. But I will say that dark energy is a research topic. Dark matter is a research topic, both very important research topics of the current time. The obvious question to pose is, what is the dark matter? It's hard to determine what something is made of when you cannot see it. In recent years, there have been 3 major candidates to play the role of dark matter. But I will say that all 3 candidates are just candidates, and some of them have been ruled out. There is still yet no confirmation of what exactly dark matter is, okay? Okay, so guess what is and by the way, thank you so much everybody for being here and liking and sharing and subscribing. Please do like, share, and subscribe. Really appreciate it. And thank you so much, Acacio, for the super chat. I really appreciate you. It was Acacio, right? Thank you. I liked it and I hearted it. Very good. Acacio, so much. Thank you so much for the super chat. Please do subscribe if you're here and new. Thank you, thank you. So next, my favorite particle was actually the first candidate for dark matter. So dark matter does not interact with electromagnetic radiation, does not interact with light. We cannot see it. What else does not interact with electromagnetic radiation? There is an elusive particle that we do know of, and that is in the standard model of particle physics, and that is a very light particle, turns out, and it's in the lepton family of particles. It's what I like to call a much, much lighter cousin of the electron, except it has no charge, so it does not interact with electromagnetism. So any guesses on class? Any guesses on who this particle is? I've given you lots of hints. Who wants to guess? Somebody do it. Don't be shy. Okay, I will just tell you. It is the neutrino. So this is the particle, which is part of the lepton family of particles, which is an extremely elusive particle because it too does not interact with light. And that was the first candidate that they thought of when it came to Hi, how are you doing? When it came to figuring out, or when it came to getting a candidate for dark matter. So the first candidate is the neutrino. A neutrino can interact with other particles only via gravity or the weak nuclear force. So once again, there are 4 fundamental forces of nature. These are gravitation, electromagnetic force, weak nuclear force, and strong nuclear force. The neutrino is a type of particle in particle physics in the lepton family, which only interacts via the weak nuclear force. So it is actually extremely elusive. It's very difficult to detect. So the weak nuclear force is weak indeed. The overwhelming majority of solar neutrinos zip through the sun as if it weren't even there. Since neutrinos snub photons, just as they snub other particles, they are a possible candidate for the dark matter if they have enough mass. So people thought, astronomers thought, well, we do know of one particle which is very elusive, which is very difficult to detect and which does not interact with light, does not interact with other particles, except through the weak nuclear force. So that is the neutrino. And when neutrinos were discovered and then dark matter was discovered, people were like, oh, is dark matter basically just neutrinos that we didn't know about or something, and neutrinos that we didn't account for somehow? So later on, also, they found that neutrinos come in 3 flavors. These are called electron neutrino, muon neutrino, tau neutrino. And these have different masses. So even though the mass of the neutrino is very small, but these 3 flavors of neutrinos actually have different masses. So although the exact mass of each flavor has not been determined, there are fairly strict upper limits on their mass from various experiments. Because it's so low, like the mass of the neutrinos is so low, it's difficult to get the exact mass, but we do have upper limits. Even though neutrinos are very common particles, they are actually part of many, 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 if not all, nuclear physics reactions. Their low masses mean that they contribute at most a few % of the dark matter present in the universe. So we think that because of its low mass, the neutrino, even though a promising candidate to think about, probably, possibly, for sure, cannot be all of the dark matter. So there's too much dark matter mass and neutrinos too low mass to really account for that. So guess what? Because the neutrinos did not help out in giving us a dark matter candidate, the next candidate that we have is the WIMP. It's called WIMP, which stands for weakly interacting massive particle. So it's kind of inspired by the neutrinos, but remember, the issue with the neutrino was its low mass. So now we've got more massive weakly interacting particles as a candidate. So now let me just say that WIMPs are purely theorized particles at this point. There is a ongoing search for WIMPs, several efforts to search for WIMPs, but this is a dark matter candidate that we don't have yet. Neutrino was a dark matter candidate that they considered, and it is truly a particle that definitely exists and whatnot. This WIMP candidate is theorized. If it is discovered, that will be great. It will give us dark matter, particle nature of dark matter, but it is not yet discovered, okay? But supersymmetric extensions to the standard model of particle physics predict massive particles that interact only through the weak nuclear force and through gravity, of course. Think of them as the obese cousins of neutrinos. Particle physicists give these hypothetical particles names like photinos, gravitinos, axinos, neutrinos, and gluinos. So this is sort of coming also from supersymmetry, which itself is a theory that needs to be confirmed. However, since they are massive and weakly interacting, astronomers lump them together under the generic label of weakly interacting massive particles. That has been going on for decades. Yeah. So we have mentioned how supersymmetry is really important and something that a lot of people rely on. Even superstring theory relies on it. And so if there is to be some confirmation of supersymmetry, that would be good, because more than one thing is relying on supersymmetry. And this type of stuff, the weakly interacting massive particles, is basically kind of under that umbrella of finding supersymmetric extensions to the standard model. So there's a standard model of particles. These seem to not be able to account for dark matter. So we are sort of extending the standard model to include more things that we have thought about, such as supersymmetry. And we're hoping and praying or thinking or predicting, whichever word you want to use, predicting basically these other extra particles that may be a thing that could account for dark matter. And also the nice thing about these particles is that they would have more mass. So because dark matter has so much mass, we need it to be something that is quite massive, is the thought behind this. So that's the second candidate, is stuff like that. Okay, so lots of experiments searching for the WIMPs, did not find it. Okay, next let's talk about the third candidate of dark matter before we wrap up for tonight. This is going to be the macho. So I think because the one candidate is the WIMP, some other people came up with this other candidate and called it the macho. So this stands for massive compact halo object. It's an acronym, massive compact halo object. And machos are basically dim, dense objects with masses comparable to or somewhat less than the mass of the sun. So think about compact objects like black holes, neutron stars, those types of things, but with mass less than the sun. Brown dwarfs or old, cold white dwarfs, so white dwarfs that are old and cold, so not much luminosity, because remember, we can't have these things have luminosity because that's the whole point. Dark matter is very dark, so whatever is to account for it has to be cold, old, dark, dim, those types of things. Neutron stars and black holes can all be machos if they're located in the halo of our galaxy. So compact halo objects. It has to be in the halo because that's where we see all of this extra mass. It has to be dim, dark, not luminous because we don't see them. If there was a luminous thing there causing all this extra mass, we would have seen it. We can't, so better be dark, better be dim. And we know of certain things that are a little darker and dimmer, and these are generally those compact objects or stellar remnants, things that stars collapse to when they die. So that's the sort of idea behind this particular candidate, which is the macho. So machos, like any massive compact object, can act as gravitational lenses. So I was mentioning earlier how in astronomy, there's always a way, right, to see something. If you think, well, there's multiple ways. If you can't see something with light, then it at least should do something with gravitation. So gravitational lens is where if you have some kind of object between you and a source of light, the object between you and that source of light will actually bend the light. So bending of starlight, this is actually something that was predicted and confirmed as a phenomena. So one of the predictions of the theory of general relativity. So this is one of the big wins of general relativity, because Einstein actually predicted that bending of starlight should be happening as a phenomena. And basically, general relativity says that massive objects can bend the path of light. So there's light source behind something. There's an object here, we're here, light is coming here. It's actually going to bend because of that massive object that's in between, because massive objects can bend space-time. Remember? So GR is all about the curvature of space-time, and gravitation is explained as a bending of space-time, and massive objects will bend space-time more than less massive objects. So if light is coming towards us from a source, and in between the source and us there's some compact halo object, it should bend the light, the starlight or the source light or whatever that's behind, okay? So an early experimental support for general relativity came in the year 1919. So this was all the way back over 100 years ago, when observations of stellar positions during a solar eclipse revealed that the sun had bent the path of the starlight by an angle consistent with the predictions of Einstein. So Einstein was very much well known for this. Like I believe, was it Eddington who did the experiment? But basically they had to go someplace where they could see the solar eclipse. It was this expedition that I think that got canceled a couple times, and they did it. And it was a very big deal when they confirmed that whatever he predicted, the bending of starlight, actually was the case, was actually confirmed with experiment. It was a huge, tremendous success of Einstein and the general relativity theory. So this is what we expect even now. See, it's true even now. If there are such objects, we would expect that. So because massive compact objects bend light, they can act as gravitational lenses, making distant stars appear higher in flux than they ordinarily would. Suppose that a compact object moves directly between us and a distant star. As the lens moves toward the source, as seen from our viewpoint, the flux of light we receive from the source grows larger. As the lens moves away, again, the flux decreases to its original value. So we expect some kind of light curve where it will increase and then it will decrease as it moves away. So there should be a characteristic rise and fall if there is indeed a massive halo object in between us and distant sources. If the lens is a stellar mass macho and the source is a star in the Magellanic Clouds, so we have other sources that we can, we have sources in the sky that we can leverage for this particular experiment. So let's say the lens is a stellar mass macho, that's in the halo, the source is a star in the Magellanic Clouds, then the rise and fall typically occur over the course of a few weeks. So just based on what we know about the luminosity and the mass and everything for this lens, we would expect this. Research groups have carefully monitored the brightness of the stars in the Magellanic Clouds. So they were hoping to catch machos, which would have changed the flux of the light coming from the Magellanic Clouds if they were there due to gravitational lensing. So they were hoping to catch machos in the act of lensing. So like really, they were like really looking at the Magellanic Clouds and like, do we see any flux differences? Although lensing events have been seen, there turn out to be fewer machos than are needed to contribute all the dark matter. So there might have been a few dim objects that they did discover because of doing this, but they did not, it does not really account for all of the dark matter. So after thoroughly looking and trying to find this gravitational lensing effect, they found maybe a few dimmer objects, but nothing that comes close to accounting for all of it. So only about 20% of the dark matter in the halo can consist of machos, and this estimate might have been updated since the writing of this book. And so basically machos kind of lose as well. So it was a good idea. It was a really good idea, I think, to say that maybe there are a bunch of dimmer objects that are there, which we don't see, etc., etc. But there's just too much dark matter to account for with the machos, and so they couldn't. So pretty much at this point, what's not been ruled out completely is the WIMPs, the weakly interacting massive particles. Those particles themselves existing is something we haven't confirmed, because those types of extensions from the standard model of particle physics is something that we're still working on and we have not confirmed. So that's where we are right now as far as the candidates of dark matter go. Hopefully this shed some light on dark matter, figuratively, because I know that dark matter does not interact with light. But that's what I have for you tonight. Thank you so much, everybody, for joining and for liking, sharing, subscribing. I do hope that you enjoyed. This is a sort of nightly physics live that I do, hopefully at least a few nights per week. And hopefully I'll see many of you again next time. And if you have any questions, by the way, put it in the chat. So if you are going back, or if you are joining later, or if you see this later on, then please do rewind and see the full live. We talked about evidence of dark matter in our own galaxy, as well as some dark matter candidates and whatnot. Thank you, Last Independent. Entanglement, activation, dark energy entangles across vacuum. Quantum gravity. Yes, so quantum gravity is, of course, we don't know what that is, but it is a topic that people want to hear more about. Sort of the quantum nature of gravity, the particle nature of gravity. So particle physics does not address gravitation very well or at all. So definitely there is a lot of room for improvement when it comes to addressing gravitation with quantum or with particle physics. And any ideas are welcome. Galaxies orbit around something. That's a great question, and I don't think I know. That actually makes sense if they do orbit around something, but I don't know. And actually, I think what you're asking, is also to do, so there's a couple of things. So I'll say this. There's a couple of things. So one thing is large scale structure in the universe. So one thing is that we have to understand exactly how we even got galaxies. Like, we know that galaxies come from those overdensities in the smoother universe, and in some points gravitation was allowed to win, and probably dark matter played an important role in the formation of the first galaxies. So the one part of the answer, I think, has to do with dark matter, and the other part, interestingly, has to do with probably dark energy, because dark energy makes the universe expand, and so it's kind of putting distance between things as time goes on. So there's also that. So basically, I don't know if galaxies are orbiting something. I do know that there is a lot to understand about large scale structure, and the distribution of matter in the universe is not random. And probably both dark matter and dark energy have a role to play there. Okay. Entanglement, activation, dark energy. Armuniu. Are you writing Einstein's equation for me? By the way, if you're interested in a more mathier live stream, we talked about Einstein's equations and general relativity in one of our live streams here a while ago. I believe it's called, I think I just called it Einstein's equations, and we talked about the the Ricci tensor and Einstein's equations and everything like that in that particular live. So you might like that. So, and we set up the math that you need for GR. So because general relativity follows a different geometry than our usual Euclidean geometry, there is sort of a different kind of math setup that you need for doing the general relativity math and equations. So we kind of did some work to set that up and some of these types of things. So if you're interested, I do have a live, at least probably a couple lives that have those types of math things in it. Okay, go ahead and find that if you will. Hello. Hello, Crazy Sick Wine. How are you doing? Did I say hi to everyone? Hi, David. Hi, Crazy. Hi, Steven. Hi, Acacio. Acacio, thank you for being here and doing the super chat. Who else wants to do a super chat? How long have you been on? Quite long. I'm almost done. I'm wrapping up now. Just looking for any questions or anything like that. Last comments. Any last comments, everybody? I've been on for 82 minutes. I just saw the timer. Any last questions, comments, thoughts, love, hate? Let me know. I'm not sure that I probably won't be on tomorrow. I have plans. And I will be posting a lot of shorts videos and doing like a schedule of shorts and videos coming up. So please do check those out. Oh, you didn't get a notification. I also shared the live on my channel. You should rewind Crazy Sick Wine because today's discussion was quite interesting. We talked about evidence of dark matter. You should rewind. Can you rewind? Thank you for liking, by the way. Thank you for liking, sharing, and subscribing. Can we get 20 likes? Whenever you see this, please do like it. So, yeah. Rewind. So, let's make the channel grow. Oh, of course. Let's make the channel grow. I know, right? Can I get some help, you guys? Oh, Acacio, can I also ask you to go hype my videos? Also, Crazy Sick Wine. Actually, yeah, I'm glad you're here. So, Crazy Sick Wine, Acacio, all my old friends and my reliable friends, please do go to my channel. Under the video tab, you'll see lots of videos. Find any video and can you like hype it? There's a new button now on YouTube under the video. I think you have to like swipe the comments and you see it. Well, let me just look it up right now. So you swipe and you go and find the hype button. And then you can hype it. Ah, see, here's a video of mine. See that? Now see how there's comments here? You just swipe it swipe it, and then there is a thing called hype this video. Now, if I could hype my own videos, I would, but I can't. So this is called hype this video. It's a thing under videos. Your smile always makes my day. Thank you. Here's a smile. That was scary. So on my videos, under the video, in the comments, swipe right, or sorry, no, not swipe right. Swipe left. Gosh, I don't even know how to swipe. Swipe, and then you'll see there is a thing called hype this video. Now, if you could do this on my videos, that would be most excellent. And I thank you for your kindness and help. That's how hype works. It's a new feature. Please do try it out with my videos. Hopefully that helps my videos to find new audiences and we can grow as a channel. Ugh. Oh. Can I get 5,000 subscribers? I'm so close. Can I get 5 million subscribers? Thank you.